So moving with the next question, seventh one. The kinetic energy of a freely falling body is. If you consider the freely falling body, then how much it would be? It's directly proportional to height, inversely proportional to height, or square of the time of fall, or both option 1 and 3. Let us check it out. So general formula for kinetic energy is nothing but half mv square. If you consider a freely falling body, initial velocity of the freely falling body is u and final velocity be some v. So initially when it starts its free fall, its velocity is 0, so kinetic energy will be 0. Gradually as it reaches the ground, its velocity increases to some v. Okay. So from the relation v square minus u square equals to 2as, we know that v square minus u square equals to 2as. So what is u, children? 0. What is v, children? V itself, let us consider u, and so here v, I considered it as v only, final velocity. U was 0. Acceleration, why the ball falls? Because of the gravitational energy, that is due to acceleration due to gravity, the body falls forward, and this acceleration is due to gravity g. And displacement, how much has it been displaced? Let us suppose that the body falls from a height h, then the displacement of the body is given as s is equals to h. So s is equals to h. Substituting above, we have kinetic energy equals to half m. So before that, what is v square, children? Substituting all the values in the above equation, v square is v square itself, u square is 0 square equals to 2, a is replaced with g and s is replaced with h, or v square can be replaced with 2gh. V square can be replaced with 2gh. Substituting the value of v square as 2gh in the above equation, we can find that the value of kinetic energy is equals to half m. So let us replace v square with 2gh. Then how much are you getting, children? This 2 and 2 gets cancelled. Therefore, we found that the value of kinetic energy equals to mgh. What is mgh? Mgh is it's a potential energy. Later we discuss. Kinetic energy equals to mgh. So clearly mass of the body is constant. Acceleration due to gravity at a given place is constant. Hence kinetic energy is proportional to h. So kinetic energy of a freely falling body is directly proportional to the height of its fall. So of course option 1 is true. But if you observe carefully, in fourth option 1 and 3 are also true, it was given. So if 1 is true, let us see if it is second option is true or not. No. Is it directly proportional to h or inversely proportional? Directly means both should be in the numerator. Inversely means one is in numerator and the other is in denominator. So it is directly proportional. So this statement is of course false. Let us check whether the third option is true or not. Is directly proportional to the square of time of its fall. Where is time, children? Again from the same formula, let us consider that it takes t amount of time to start for the complete free fall. Let us consider that from here to here, it takes t amount of time to reach. So again from the kinematic equation, we know that v is equals to u plus at. As v, I have considered as v, u as 0 and the acceleration as g. Let us try to find out the value of t. So substituting here, v equals to 0 plus gt, or t can be given as v by gt. Value of t can be given as V by G, or simply leave it children. Instead of V, let us replace it with V equals to GT. Again, from our formula, what is that? As we know that the kinetic energy of a body is given as half mv square. Substituting the value of V is GT means V square will be equals to G square T square. So, for a given body, half of course is always constant, mass is constant, gravity is also constant. Hence, clearly we can say that kinetic energy is proportional to T square. Here we observe that kinetic energy is proportional to height of its fall, and here we observe that kinetic energy is directly proportional to the square of its time. Hence, both options 1 and 3 are true. There proportional to h, here proportional to T square. Consider the following statements. Two statements were given children. Linear momentum of a system of particles is 0 and kinetic energy of a system of particles is 0. Then we need to consider which among the statements is true. Whether A implies B or B implies C or anything related to that term. So before discussing in detail, let us go with the clear data. The first one is if you consider whether it is a momentum or a kinetic energy, it only depends on two factors, that is mass of the body as well as velocity or speed of the body. So, but we know that mass of a body is always positive. For any body, you consider mass can never be negative or 0. So, mass always takes positive values. Whereas, for velocity, the velocity of a body can be positive, negative, or it can also be 0. So, velocity of a body can be positive, negative or 0. So, if you want to find out the momentum of a body, momentum of the body can be given as mass into velocity. So, this mass as always positive. So, positive into positive or positive into negative or positive into 0, then the momentum of the body, it can either give a positive value, a negative value or a 0 value. Children, I repeat, if mass of a body is always positive, but velocity of a body can be positive, negative or 0. And hence, the momentum of the body is product of the two. So, if velocity takes a positive value, momentum gives a positive result. Velocity takes negative value, momentum will be negative. If velocity is given a 0, then momentum will be 0. Similarly, if you would like to find out the value of the kinetic energy, okay. So, momentum of a body can be positive, negative or 0 because momentum is a vector quantity. So, it can take in. But kinetic energy is a scalar quantity. So, since kinetic energy is a scalar quantity, only two possibilities are there. Whether the formula for kinetic energy is half mv square. So, velocity, kinetic energy can never be negative. It only takes two values. Suppose if V is positive values, or it can also either be 0 values, but never a negative values. Even if you take minus V also, that will be V square only, positive only. So, this kinetic energy will give either positive values or 0. So, I hope the points are clear. Mass is positive, velocity can be positive, negative, 0, momentum can be positive, negative, 0 and kinetic energy can be only positive or 0. Just keeping in this mind, let us consider for the system of particles. Now, let us go with the concept. For the system of particles, the kinetic energy of the system of particles is generally given as half mv square. Half system means summation of all the product of masses and velocity square. Half mi, kinetic energy of the system of particles, KEI equals to half sigma mi vi square. So, for the total complete system. First of all, let us start with B and then we'll go for the statement A. First of all, let us try to analyze the statement B. So, what does B indicates? If kinetic energy of a system of particles is 0. So, if kinetic energy of a system of particles 0, this implies that this product half sigma mi vi square must be 0. When does this equals to 0, children? half not equals to 0, sum of the masses is. This can be possible if and only if Vi is equals to 0. So kinetic energy will be 0 when only velocity of the particles will be 0. If velocity of the particles is 0, then this implies and implied by the momentum of some of the particles will be mass into velocity of the particles. This is equals to mass m times of velocity of the particle is 0. So anything into 0 will be 0. So clearly we concluded that if kinetic energy of a particle is 0, there is a possibility that momentum of a body can also be 0. This is what we have cleared. So if kinetic energy of a particle is 0, we observe that momentum of a body can be 0. So if kinetic energy, that statement B, that is if kinetic energy of a system of particles is 0, then the linear momentum of a system of particles can be 0. This implies B implies A. B implies A. Where is B implies A? So this must be wrong statement. Here because does not imply give. Here also wrong statement, does not imply. B implies A. This might be true. B implies A. This might be true. So we have to check whether third option or fourth option, which one is true. So very clearly we can conclude that the first two statements are options are wrong. So now let us check for option A. So moving to the option A, let us see what happens. What is given, children? Linear momentum of a system of particles is 0. In order to understand this carefully, let us consider a system. Consider a system which consists of only two particles. Only two particles. This is to understand A. So, particle 1 and particle 2. Let us suppose that these two particles are having same masses, that is equal masses, but one is traveling in this forward direction, whereas the other is traveling with in the backward direction, both with the same velocity. This is V and here also V. Okay. So we have considered two equal masses traveling in opposite direction. So in this case, if you consider the total momentum of the two bodies, then the total momentum of the two bodies can be given as mass into velocity of the first body minus mass into velocity of the second body, because they both are traveling in opposite direction, and this is equals to 0. So clearly what we said, linear momentum of a system of particles is 0. So if linear momentum of a system of particles is 0, so clearly if Pi equals to 0, let us see whether Ke will be equals to 0 for the same case. Now if you want to measure kinetic energy, the value of the kinetic energy of the system of particles is half mv square plus half mv square. This is equals to 2 times of half mv square. So clearly this is not equals to 0. So what we observed that if momentum of a system of particles is 0, the kinetic energy of the system of particles need not be 0. Okay, that means A does not imply B. A does not imply B. So where is the correct option? Here it was given as A implies B and here A does not imply B. As earlier we said that both statements are true, but here this statement is false. Hence, this must be false. So, the only correct option is that A does not imply, if P momentum happens to be 0, kinetic energy is not 0 in this case. But if kinetic energy becomes 0, momentum of the system of particles will be 0 only. Hence, A does not imply B. If momentum of a system is particles is 0, kinetic energy of a system of particles is not 0. But B implies A. If kinetic energy of a particle is 0, momentum of a particle will be 0. So the correct option is option 3. So just go through this carefully, children, then you can get into me. Okay. So here is one consideration and here is your another consideration for the both statements, and that is a generalization. So moving to the next one, 9th question, internal forces. So what is given, children? Internal forces can change linear momentum as well as kinetic energy, linear momentum but not the kinetic energy but not the linear momentum, or neither of them. So what internal forces are? So internal forces, just now we have discussed that because of the momentum and mass is always positive, whereas velocity can be positive, negative or zero. So linear momentum of a body, of the system of particles, the two system of particles what we have considered is, so if you consider a system of particles, two particles having equal masses moving in opposite direction with velocity v, we concluded that total momentum is zero. So instead of that, what we consider here is, let us consider a body of mass m initially at rest. Let us also consider a body of equal mass which is also at rest. So let us consider two equal masses which are at rest condition initially. Then what is the initial momentum of the two system of particles, children? Initial momentum of the system is equals to half mu square, mass into velocity. What is mass into velocity? M into 0 plus for the second body also m into 0. This is equals to 0. Now, later on, let us consider that these two bodies are moving with some velocity. It is moving with velocity v in the forward direction, and the other is also moving with velocity v in the backward direction. So, both are moving in the opposite direction. In this case, the final momentum of the body can be written as mass into velocity in the positive direction, and again mass into velocity in the backward direction. This will be mass into velocity. So this is again 0. So very clearly the total momentum of the system initially is equals to the total momentum after. Okay. Then very clearly we can say that the Pi is equals to Pf. Okay. Hence, the total momentum of the system before and after is taken as 0. So, before and after, the total momentum of the system can be taken as 0. So, whenever the total momentum of the system is 0, we can say that the momentum of the system is conserved. Momentum of the system is conserved. But the same will not happen with the help of kinetic energy. Let us also consider the kinetic energy, children. So, what is initial kinetic energy? Ki equals to half m u square is 0 square plus half m v square. Again, second body is g square. For the total body initial kinetic energy, and this is equals to 0. Whereas, the final kinetic energy equals to half m v square plus half m v square, and this is not equals to 2 times of half m v square, and this is not equals to 0. So clearly the total initial kinetic energy is not equals to total kinetic the total final kinetic energy. So that is K initial is not equals to K final. Here the total initial momentum is equals to total final momentum. So, hence we can conclude that it is conserved. But here the total initial kinetic energy is not equals to total final kinetic energy. Hence, we can say that the system is not conserved. So, very clearly, the linear momentum of the system is conserved, whereas kinetic energy of the system is not conserved. So that means kinetic energy is converted into other form of energies, maybe heat energy, maybe light energy or something like that. And this can be observed during the explosion. Whenever a bomb is exploded, the kinetic energy of the system increases. Similarly, we can also conclude another example is regarding the inelastic collision. During inelastic collision, the kinetic energy of the system decreases. That means this kinetic energy is not conserved. This can be interchanged to some other forms of energy. Sometimes kinetic energy may increase and sometimes kinetic energy is decreases but is not constant or not conserved. So we can conclude that kinetic energy, that means some internal forces are acting. Okay, so clearly internal forces in the kinetic energy, so it can change, the internal forces can change the kinetic energy, but they cannot change the momentum because momentum is conserved. Therefore, the correct option is kinetic energy changes, but momentum does not change. So, internal forces can change what? Kinetic energy, but not momentum. Cannot change linear momentum. No. Internal forces can change kinetic energy, but not linear momentum. So, third option must be true. Is that clear, children? So, what we have concluded is that first of all, consider example, calculate the internal momentum, final momentum. Let us see whether it is conserved or not. Similarly, for the same example, let us consider the kinetic energy, total initial and final kinetic energy. Here it is conserved, not conserved. Conserved means who is acting, internal forces are helping them for its changes.